exponential growth and decay. Once you start studying exponential functions, at some point, I hope, you're going to be learning about exponential growth and decay. So it is extremely useful and it has numerous applications, from population growth, nowadays, virus kind of growth within a population. It has growth in terms of money, so compounding, sometimes people refer to that. It can also have exponential decay, which is not growth, but obviously some kind of a decline. Now, when you have your exponential function, so the one that you see right here, I'm going to just kind of write it out. So here is my exponential function that I chose. F at x is equal to a multiplied b to the exponent of x. Now, in the introduction to these exponential functions, now maybe if you've missed it or if you need it, I'll put up a link up above there. We had certain things and certain characteristics of these exponential functions that came out at us. Now, for this video, I'm actually going to make some assumptions because it's going to be related to exponential growth and decay, and it's going to make it a little bit more realistic. So one of the kind of assumptions that I'll make is that I'll put the domain on the input, so on the x. I'll say that the domain is basically restricted, so it can be any real number. However, we're going to restrict it so that it is basically anything greater or equal to 0. So that's one of the restrictions that I'll put. The other restriction that I'll put, just so that it actually kind of shows us some application within exponential growth and decay. This doesn't have to be, and later on, as you keep studying past kind of grade 11 or so, maybe you'll have other applications, but I'll make another restriction here for us, and I'll say that a is going to be greater than 0. So we can't have a which is 0, obviously, because it would just nullify the whole function, and we won't make it negative so that those exponential functions are not going to be really reflected over. So we're going to keep it as positive. Now, one of the key things in these exponential functions that we've realized is that there was kind of two instances for this b to take over, right? Where we had these cases for b, where b was either greater than 1, and in those instances, if it is greater than 1, so it can be anything, it can be 1.1 or 1.01 even. In those instances, what we've noticed was if we would graph these, so if I'm going to kind of graph or at least sketch this a little bit for us. Okay, so let's say this is my, say x, okay, that's my output of the function f of x. Now I am restricting it for x which is greater or equal to 0. So what I noticed is under this situation, well, first off, if x is equal to 0, I know that I would have been starting, okay, so because b to the 0 is just 1, and that means 1 times a, so I'm going to be starting at a here. So in all of these cases that we will have is we're going to be starting at a at some point. And now as b gets bigger, okay, or sorry, as x gets bigger, so as x continues onwards, what we notice in this case where b is greater than 1, we've noticed that this starts to kind of grow and then just kind of blows up on us. So this is the actual growth that we are referring to in terms of the exponential growth. And it is called exponential because of the fact that our input is acting on our b as an exponent. So it's exponentially growing on us as x gets bigger and bigger and bigger. Now, the other case that we had, so this was the case when b was greater than 1, but the other case that we had was we had the case when b was basically between 0 and 1. So it was somewhere along within here, which basically meant that it was less than 1, but it was greater than 0. And what we've noticed in those cases, well, if we would have x equal to 0, we still would start at a, so it would look very similar. But now, instead of our actual functions kind of growing, what we notice that in this case, if you would start plotting this, this would start kind of going in this direction, and it would start to approach basically 0. And this is called decay. So it is decaying towards 0. And that is because our b is stuck between 0 and 1. And no matter what x is, okay, so as it carries on, it's going to start to decay. And we gave some examples of these. So, I mean, we can, fix these b's. So, for instance, I can put b is equal to 2, all right? And then I can say, b is equal to a half. And then if we would plot this out, we would notice that we would have this particular pattern. And it doesn't matter what a is. So let me plot this for you. I'm going to pull up decimals just so that we can kind of see and get some feel for this function again in terms of its growth and decay. And then I'll talk a little bit more. All right, so welcome back. So what I did was I just plotted here in decimals. So our a times our b to the x. And notice I put, if you want to put some restriction, you can put it in the braces. So I put x is greater or equal to 0 here. So our function actually doesn't continue on into the negatives. So we're assuming that we're going to have our x kind of just growing, right, as it gets bigger and bigger. And now I fixed my a, which is equal to 1, and you will notice that indeed that's where you would start. So you would start at 0.1. And now no matter what a is, now we know from kind of exponential functions, if a is positive, we know that we're going to be going in the positive direction in some particular way, depending on what b is, okay? But here at b is when the x is equal to 0, and no matter what a is, all that's going to happen, okay, is that we're going to be moving, okay, our basically starting point. So notice if a is 4.2, you notice that that's exactly where we start, right? And then I can just kind of move this around wherever it is that I like, and have that starting point. So it doesn't really matter what this a would be. That's going to be just our starting. The idea for me to you in terms of explaining is the concept that it's growing, that it's exponentially growing. So growing is something that it's increasing, but of course we have numerous functions that grow. You can have a line and it's growing, right? But it's growing linearly because it's growing at the same rate with the same exact slope. Here, what's going to happen is that this growth is going to start speeding up, okay? And the exponential function has this amazing property where as the x gets bigger and bigger, if b is greater than 1, it really starts to blow up on you. So if I, kind of go out in here, you notice that it very quickly starts to just skyrocket upwards. And that's the exponential growth that we see. And this is no matter what the b is. Now, if b is greater and greater, the exponential growth becomes bigger and bigger and bigger. And that is something that you would have seen, with any b that just gets bigger and bigger, because now all of a sudden our exponent is acting on that b. So, notice that if b was equal to 2, if you square it, it was equal to 4. But if b is equal to 5, or let's say 5.1 like here, and you square that, it's going to be more than 25 for exactly the same x, okay, which x is equal to 2. So it really just skyrockets on you pretty quickly, right, as you carry on. Now, if b was between 0 and 1, so if I put it between here, okay, so notice if I put it at 1, it's going to go, and it's going to flatline there, okay? And it's going to flatline there because of the fact that if b is equal to 1, no matter what x is, right, it's just a flat line. And we talked about that in terms of the introductions. But, if I make this b, and now let's say I fix it between 0 and 1, okay, in this way, okay, so what you notice is, let me kind of zoom in here just so that you can see, okay, so no matter what this is, okay, so as b gets smaller and smaller, you have this decaying, okay, look, where our exponential just starts to really tries to get closer and closer to 0, faster and faster and faster. Now, if b gets closer to 1, you notice that it doesn't decay as quickly, but it still decays over time and eventually does get into, that 0 range and gets closer and closer. So that's what happens within here. So this, okay, when b is between 0 and 1, it's called exponential decay because it's always decaying towards 0. Now, if we are greater than 1, so if I put 1, let's say I'll put here between 1 and 10, just to prove a point, okay, if we do this, then we notice that it just starts to skyrocket, okay, on us. All right, so here, no matter what it is, it just starts to skyrocket upwards. So that is called exponential growth. Now, before I actually complete this video, so I mean, the concept of growth and decay should make sense to you intuitively, you know, something growing, something decaying. But I want to rewrite our function. So we have written out that f of x was equal to a multiplied by b to the x, you know, and we have those two cases where b is greater than 1, and then when b is basically between 0 and 1. Now, in various applications, which I will do, okay, so I'll just kind of, maybe I'll link, okay, some applications within there, okay, once they go up. But within various applications, we actually like to write these growth and decay functions a little bit differently. So instead of writing them as a b to the x, which completely is an exponential function, it's fine. But what we sometimes like to do is we like to say, so we don't do anything with the a, that's just our starting point. Okay, so we had our starting point right there. But we transform this b, and we actually say that b is 1. And I'm going to first start, okay, with a plus some r, okay, and it's raised to the x. So this is my new b, all right? And there's going to be two instances. So this one is with a plus, and it's going to designate basically our exponential growth. So instead of having just a b and then stating that b is greater than 1, what we like to do on occasion is we like to rewrite this function as a, and then in brackets 1 plus r, where our r is basically greater than 0. Because notice, if r is greater than 0, then what will happen is that you're going to have 1, okay? So you're going to have your 1 plus r, which is always going to be greater than 1. This means that this is the case when b is greater than 1. And that actually designates our exponential growth. And this r that we put in here, this is actually a rate. So I want you to keep that in mind. You know, a rate is basically, you know, some kind of a percentage, okay, in terms of growing. How quickly does something grow? You know, and then we will say that maybe something is growing at 5%, or maybe it's growing at 10%, or 50%, or 200%. It doesn't really matter. But I want you to keep that in mind. And this plus that you see right here is actually going to designate exponential growth for us. Now, if I would rewrite this same function, but instead what I would have done, I would have said that this is a, and I would say 1 minus r to the x. Now, in this case, I have to be a little bit more specific. So what I'm going to do here is I'm going to say that r, okay, so we know that r is going to be greater than, okay, so it's greater than 0, but, you know, we want to try to keep it, okay, so that it is, you know, so in this case, okay, so that we have that. So it's going to be greater than 0, but it's going to be less than 1. Because if it's 0, then, you know, we're stuck at just having 1 to the exponent of x. And then if we have 1, if r is equal to 1, okay, then it goes 1 minus 1, which is 0, and then it just zeroes off, okay, our function, which we don't really want. So this is the second instance. And now this, okay, and I'm going to highlight here the negative. So when it's negative, it's basically some kind of a decay. So again, it is some kind of a rate, so that r represents a rate. But maybe it's decaying at a certain rate. You know, maybe it's decaying at 2% or 5% or 25%. And you're going to see that in some applications. So I just want you to keep these two things in mind. So in general, we have two kind of instances of cases. We're going to have the case, and maybe I'll write them out in two different ways. I'm going to say that in general, we say that growth, instead of writing b, we kind of do this. And sometimes the x, you might see that as an n, okay, in terms of the variable. So the variable input, it doesn't really matter. And this second one, okay, so within here, sometimes we see 1 minus r, okay, to the x. So r in here is greater than 0. And then in the second case, r is greater than 0, but it's less than 1 because we don't want to start going into the negatives, okay, within here. And if you would plot this on decimals for these values of r, you would notice that, okay, the first case, this one, just represents exponential growth, okay? And the second one, this one, is actually exponential decay. That's what you would see within here. So let me plot it for you again, just so that you can see. All right, so here is your function. So this is your exponential growth. So notice that for any r, okay, so that we will have, so for any r which is greater than basically 0, so here's 0, which is going to flat line, because then it's just 1 plus 0. So now if I increase this, okay, and if I make it bigger, okay, then it looks exactly like an exponential growth. That's what happens within here. But now notice if what I did was within here, if I said minus, so if we're going to say minus in here, okay, and let me just fix this so that it's between 0 and 1. So if I said minus, it's going to be, okay, so in this case, now it's going to be a decay, okay, and that's exactly what happens. Notice that. All right, and it just decays faster and faster the bigger the r kind of becomes, okay? So that r is going to represent a rate for us, how quickly something is growing or how quickly something is decaying. And that's where I want to kind of finish this video as an introduction to these exponential growths and exponential decays. I hope that it gives you some light and, maybe you can think of some of the applications. And once you see some applications, then these two actual functions, these are still exponential functions, are going to play quite a big role. Okay? So see you then. Take care, everyone. Bye.